What's up, guys? Today we're doing a video on a couple more applications for logarithms, and these two cases are pH, which is chemistry, and earthquakes or seismic events, specifically the Richter scale, which is physics. And I'm not going to get too far into the science behind all this, but we are going to look at the math and how it's an application of exponents and logarithms. So I wrote the formulas at the top there, and you need to make sure you have these. Usually they'll be given in the problem, but you want to go and write them down anyways, just to make sure you're familiar with them. Of course, when you take physics class or science, I know when you take chemistry, you're going to need these for sure. I hear from my students all the time that a lot of times they've used this already by the time they get in my class. And I'm sure that they would make you memorize those formulas. Anyways, the pH of a substance is the negative log of the hydrogen ion concentration. Okay, and I'll let your chemistry teacher explain to you what that means. I'm certainly not going to mess it up here, but this is a formula that we can understand. pH is the negative log of the hydrogen ion concentration. This is just a number, and this is just a number, and they're related by this logarithm. Now I can rewrite this equation so that the hydrogen ion concentration, we'll just call it H+, that is by itself. If we rewrite this, remember that with log, if you don't put a base, then the base is 10. So I can rewrite this. Just move the negative sign over here, multiply by -1. So imagine that the negative sign were over here. Then you just say 10 to this power equals the hydrogen ion concentration. Well, that's what this formula is, okay? So this formula is the same formula, just rewritten as an exponent in order to get the hydrogen ion concentration by itself instead of the pH. So we'll go ahead and do the examples for that. So the examples of pH. So if I want to find the pH of a substance with a given hydrogen ion concentration of 3.4 times 10 to the -6. Now that's scientific notation. You should have seen this before. What this is saying is 3.4 times 10 to the -6. So you've got 6 zeros in front of this. So in other words, we need to move the decimal place to the left 6 times. Okay, I think that should be 5 zeros. You move the decimal place to the left 6 times. So there would be 5 zeros in front of this number, okay? 0.000034. Okay, in other words, it's a very small number. We can put that in the calculator like this. So we just type in our equation here, put this right into the calculator. pH equals negative log, parentheses, 3.4 times 10 to the -6. Just type it in the calculator just like that. Press enter, it'll tell you 5.46. So the pH is 5.46. On the next problem, we're going to work the other way. It says find the hydrogen ion concentration. Sometimes they may use a symbol, sometimes they may write it out, for a substance with a pH of 9.2. So we're just going to say the hydrogen ion concentration equals 10 to the -9.2 power. Put that in the calculator. We get an answer in scientific notation. 6.3 times 10 to the -10th. That just means you got to move the decimal place to the left 10 times. This is a very, 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 very small number. Okay. All right, so in earthquakes, and really it's not just earthquakes, anything that shakes the ground basically. So nuclear bombs, asteroids, anything that can cause a big impact or make the earth shake. This is what they use to measure it. It's a logarithmic scale, okay? So again, remember that when we're talking about logarithmic scales, an increase of 1 means something is 10 times stronger. So if we talk about a magnitude 7 earthquake, that's pretty bad. That's a strong earthquake, okay? Magnitude 7. Imagine one magnitude higher, magnitude 8. Magnitude 8 is 10 times stronger than magnitude 7. And magnitude 9 is pretty much cataclysmic. So it's very, it's very quickly growing. These are logarithmic scales. It's based on a power of 10. So every time R increases by 1, the relative size is getting 10 times stronger. If you want to have a fun read, get on Wikipedia, look up the Richter scale. And they've got some famous events throughout history, and you can actually see what they registered on the Richter scale, including the impact that killed the dinosaurs, or what they expect the magnitude was. Very interesting. Anyways, find the relative size of an earthquake, a 7.8 magnitude. We're just going to use this formula. It's a very simple formula, probably easier to think about than pH because there's no negative sign. All right, so the relative size is going to be 10 to the Richter scale, whatever the magnitude was, 7.8 power. You just put that in the calculator, and we get 63,095,734.4. And you can write some of these numbers in scientific notation as well. Whichever way you'd rather do it is fine with me. find the magnitude of an earthquake with a relative size of 40 million. Okay, so in this case, they gave us S, we're looking for R, so we need to rewrite the equation as a logarithm. So I'm going to say, since the base is 10, I'm going to say log base 10, which means I don't need to write it. And these switch places. The R is by itself, the 40 million is inside the logarithm. Just put that in your calculator and you get 7.6.